Welcome to section 3.5, straightening up the circle. We're going to explore the infinite within geometrical objects. Question of the day: are there more points in a square than on a line segment? So pause the video here, make a prediction, draw some pictures. We're going to answer this question, so let's see. We'll come back to your thinking and see what you got. All right, let's start with just two line segments. Are there more points in line segment B than in line segment S? So we've got these 2 points here, and maybe you're thinking, yeah, there are more points in line segment B. It's clearly longer, right? And maybe you're even thinking, hey, maybe because the B is bigger, it's already bigger. And I'm pretty sure nobody thought that, but maybe you did. But let's think about this idea here that yes, there are more points in segment B than segment S because it is longer. And this is some excellent incorrect thinking. So this is what I would originally think, right? I would say, okay, let's use one-to-one correspondence. Let's line it up and let's see if we can match a point to point and then call it. And when I line it up 0 to 1 and I match point to point, there's no point here to match. And so I would say that, yeah, segment B is longer, but this is actually incorrect thinking. And so let's think of this another way. Why is this wrong? So recall that for two sets to have the same cardinality, there must exist a one-to-one correspondence. We have never asked, what does it mean for two sets not to have the same cardinality? It means it is impossible to find a one-to-one correspondence. We didn't show that it was impossible. We just said that this one pairing doesn't work. So the point is that just finding a particular pairing that is not a one-to-one correspondence is not enough. Finding a pairing that shows that it doesn't work. It does not show that one-to-one correspondence doesn't exist. It just shows that that pairing doesn't exist. So all that this shows is this is not one-to-one correspondence, but there still could be one-to-one correspondence. So I'm actually going to tell you that those two line segments have the same cardinality. So go ahead and pause it and just see if you can make sense of it. Draw some pictures, connect some lines, see what you can see, and then press play when you're ready to see how this works. Okay. So we've got these two line segments, and I've gone ahead and I've lined them up to match. Now what I'm going to do is I'm going to draw a line that passes through both lines, and I want to encompass the whole line. And I am going to use a ruler here just because my art skills are just not wonderful. So okay, there's a line that goes through the 0, 0s, and here's a line that goes through the 1 and the 3. All right, so I have drawn a line, and those two lines, they're going to intersect, and they actually intersect right here. So let's call this point P. All right, so now I've got these two lines here, and the idea is that I want to see where every point on S, if it can hit a point on B. So let's start by saying, okay, let's call a point on S. Let's call this point W here. Where will this point W hit on B? Okay, well, let me get my ruler out, and let's say, okay, that point W is gonna hit right there. Let's call this H. That's where it hits H. Okay, what about another point on S? Let's call this A, another point. Where's that gonna hit on B? That could hit right there. What about another? And I could just kind of keep going with this, right? I mean, I'm gonna be able to hit a point on S and a point on S and a point on B every time. So I can show that a point on S does have one-to-one correspondence with a point on B. It's going to hit at one point every time. Well, now let's go backwards. How about points on B? Will those correspond back? And I've actually only shown it in one direction, right? How about if I start with a point on B? Is it the same idea? So let's see here. If I start with, let's say, point R, is that going to hit on S? And if I go through that point P, yeah, it hits right there. Okay, how about another point on B? Yep. And if I do this method every time, I can actually prove that any point on B is going to hit on point S. So what I've shown is one-to-one correspondence, that there is always going to be a point B on point B that corresponds to a point on S, and a point S that corresponds to point B. So therefore, those are one-to-one correspondence. We found that they have the same cardinality. And just because this is from the book, and I used a ruler, so I think we're okay, but just in case, there you go. All right, so what about these two? We saw line segments, right? We saw this line segment, one line segment, and another line segment. Well, what about an entire line that goes on forever and a line segment with holes? This line segment is not defined for 0 and 1. What about those two? Is the cardinality of the set of points in R, all real numbers, greater than the cardinality of the set of points in S, this little line segment? So we're basically asking, is there a one-to-one correspondence between the set of the points in S and the set of the real numbers R? And I say the real numbers because that's a number line. And I'm going to tell you that one-to-one correspondence exists. So I want you to pause it here and see if you can figure it out, see if you can draw something, and then press play when you're ready to see how that looks. All right, so first, we're not going to change the cardinality of S if we bend it a little bit, if we just change its shape. So look at all the different ways we've kind of changed the shape of S, and we can actually just round that up right into a circle. And that's exactly what we're going to do. And then we're going to line up that circle. Now the circle sits on the line at its south pole. Let's say that's its south pole. And again, remember that its north pole is not defined, right? That 0 value there is not defined. And it touches the line at exactly 1 point. In fact, it touches it at 0. And so we're going to draw lines again to show the one-to-one correspondence. So let's let A be a point on the circle minus the north pole. So A cannot be on the north pole. And let's see who it gets paired with on the number line. So we're going to draw a line from the north pole hole through point A and continue until we hit the number line. And it hits down there. That line hits the number line at, let's just call it point T, right? And then, so we can say that point A and point T have correspondence, right? And that line will intersect the circle at exactly one other point. And that is the point paired with the number line. We could keep doing it. Let's call this B. Where's that point going to hit? That is just going to hit at 1 point. And we can continue on, and we'll see that there's actually one-to-one correspondence between the points on the number line and the points on the circle minus that north pole. So the cardinality of the points on the circle minus the north pole is the same as the cardinality of the points on the number line. We proved it. So what we showed there is called a stereographic projection, the one-to-one correspondence between the line segment curled up into a circle minus the north pole and the number line. The idea that we're projecting all the points of the circle minus that north pole onto the number line. The pairing rule may be thought of in another way. In some sense, we are wrapping the number line around the circle. So as we travel along the circle and approach the north pole from the left, those points are paired with the number line on the left. And as we approach it from the right, they're paired with the number line on the right. So what did we see? Not only do different line segments have the same cardinality, but even if we stretch out a line segment forever, making it the real number line, it does not increase the cardinality. So as we continue to make geometric objects with really big cardinality, let's see if instead we can increase the dimension and consider solid objects in the plane. And so that's going back to our question of the day, and we'll continue that in the next video.